FrameSpark Studios is expanding. Their new production facility is a 2-story former storage warehouse built in the 1970s. But acquiring an older industrial building means inheriting decades of hidden history and unmapped structural variables. A footprint of over 2,000 square meters offers a lot of physical potential. Yet moving fast on a renovation without understanding what is behind the walls or under the floorboards invites catastrophic risk. The physical structure is essentially a black box. Safety on this project was built months before the first boots hit the ground, starting with a deliberate, aggressive investigation into the structural past of the warehouse. This is where building information modeling replaces manual assumptions. A digital twin is constructed from site surveys and old hand-drawn calculations, creating a central intelligence system accessible to every contractor. By analyzing historical water usage records and environmental agency reports, designers pinpointed a specific flaw. The original drainage system was inadequate for a modern studio. That data directly shaped the excavation plans before a single trench was dug. Structured data also maps the threats we cannot immediately see. By digitizing the building's asbestos register, designers isolated locations containing asbestos-containing materials. The system visually flags these zones long before workers are dispatched to the roof. Consolidating site history, service layouts, and maintenance records into a shared digital environment actively removes guesswork. It forces the renovation to operate on hard facts, converting an unpredictable structure into a highly mapped, manageable workspace. When the physical work finally begins, the site must be sealed off from the outside world. Workers and visitors pass through an induction process, followed by biometric sign-ins. This establishes a strict perimeter where access is heavily restricted, and mandatory protective equipment is the cost of entry. Inside, the ground floor is stripped of its non-structural walls and original fixtures. This environment is inherently chaotic, defined by airborne dust, heavy falling materials, and intense mechanical noise. To prevent that chaos from causing injury, the site manager relies on an administrative web, risk assessments, and method statements. These documents dictate the exact sequence of how the demolition occurs, substituting raw force with a calculated step-by-step procedure. You can see these documents manifesting in the physical environment. Demolition zones are isolated by solid barriers. Workers wear particle filtering face masks. Windows and doors are propped open for strategic ventilation, and dedicated fire points are stationed at the entrance of every work area. Administrative rules do not make the sharp edges or the falling debris disappear. Instead, they deliberately box those hazards into specific, contained areas through rigorous, enforced discipline. While demolition is loud and tightly monitored, everyday tasks often escape that level of scrutiny. A routine delivery of internal wall panels arrives at the loading bay, introducing a much quieter, less obvious category of risk. Running behind schedule, the subcontractor unloads 60 large, heavy plasterboard panels. Each sheet is transferred onto a trolley, 6 at a time, then forced down a ramp and restacked onto pallets. The physical toll is immediate. Muscles and joints absorb the repetitive twisting, lifting, and heavy pushing. Rather than pausing to recover, the worker pushes through the rising aches, prioritizing speed over physical limits. Severe occupational harm does not require a dramatic fall or a sudden impact. Often, it is a slow, silent deterioration brought on by ignoring physical pain and compromising on safe lifting practices under the pressure of a ticking clock. Up in the roof motor room, an electrician is tasked with rewiring the lift motors. The method statement is clear: no live working without authorization. Upon opening a duct, they find exposed wiring in the lift shaft. To check if the circuit is live, they reach for a handheld multimeter. The insulation on the testing probes is damaged. Instead of replacing the equipment, they use a sharp knife to trim away the loose material, exposing even more of the probe. Once the wires are confirmed live, the strict controls around the area begin to unravel. A coworker leaves to find circuit drawings, casually pushing aside the protective temporary fencing. Waiting by the exposed shaft, the electrician removes their safety gloves. At this exact moment, the site manager arrives on an inspection walk. They spot the displaced fencing, notice the modified unsafe multimeter line on the ground, and immediately log the event into the site's reporting system as a near miss. Accepting damaged tools and ignoring site barriers narrows the gap between a routine test and a live strike. The site manager's intervention stops that drift before these small compromises can align into a serious incident. Outside, ground-level excavation is underway to upgrade the site's drainage. Digging through older industrial estates carries an exceptionally high probability of striking unmarked live buried surfaces. The mobile excavator cuts into the earth. Suddenly, the operator spots the distinct curve of cables emerging from the soil. The reaction is immediate. The operator kills the digging motion and contacts the site manager via two-way radio. Work halts. They retrieve the risk assessment from the cab, collect a cable avoidance tool, and physically scan and mark the ground before anyone proceeds. The operator's immediate reflex to kill the engine and hold the line until the new variable is understood is the primary indicator of the site's safety culture in action. The final challenge takes place on the building's flat roof, where an edge protection barrier is scheduled for installation. This is the most complex environment on the site. Hazards here do not exist in isolation. They overlap. The workers face a sheer drop at the unprotected edge, compounded by fragile skylights embedded in the roof surface. To move, they must rely entirely on a system of safety lanyards attached to weighted mobile anchor points. Then the final variable is introduced. The pre-construction data identified low-risk asbestos cement tiles sitting precisely at the perimeter where the edge protection must be drilled and anchored. In this overlapping geometry, a single misstep toward a fragile skylight while handling contaminated tiles creates a crisis that quickly outpaces individual judgment. The task is only survivable through the rigid adherence to the anchor points and decontamination protocols established during the planning phase. True hazard control is never a default state. It is a fragile architecture built day by day through digitized planning, strictly enforced permits, and the relentless discipline to stop unsafe drift before it takes hold.